In the previous class, we have seen the deformation of a prismatic member subjected to axial load. We got the deformation as del L is equal to P into L divided by A into E. That is what we have derived in the previous class, where P is the axial load. If load is tensile, deformation is increase in length. If the load is compressive, deformation is decrease in length. E, materials constant. A is the cross sectional area. So for calculating the deformation, we should know the A, we should know the E, we should know the P. Now coming to the problem, P means the internal resistance anywhere in the member. So to get the internal resistance, you consider the equilibrium of the member. Anywhere if I cut the member and mark the internal resistance, that is equal to the external load P. I will explain it in the next class, immediately after this derivation. So P is constant here. Anywhere if I cut here, I will get the same value of P. What about the cross sectional area? For this member, if I cut anywhere, is the area same everywhere? Say here, we are going for rectangular member. The depth is D1 here, thickness is T. Here area is D1 into T. At the other end, what is the value of area? That is D2 into T. Anywhere if I am observing inside the member, resisting area or the cross sectional area is not constant. Therefore, what is the problem with me? In the formula, what value of A is to be used is a major problem for me. Are you getting it? P is equal to, delta is equal to P into L divided by A into E. That we have proved it. While proving, we assumed that consider a member of length is equal to L, subjected to axial load is equal to P, and cross sectional area is A. Means we have assumed the P to be same throughout the length of the member. But here a special case, the deformation of a tapering member, the cross sectional area of the member is changing along the length of the member. It is not same. Then how to analyze it? For deformation of tapering bars, two categories will be there in your examination. One is rectangular one and other one is the circular one. In alternative exams, out of these two, one will always be there. That is why carefully observe this derivation. And if at all you got any problem anywhere, please stop me and clarify the doubts. Yes, what is our problem? Consider a rectangular tapering bar of length L. The length of the bar is L. At one end, its depth is D1, and at the other end, its depth is D2. And we have assumed that in the derivation, D1 is greater than D2 for this derivation. Whichever is the lesser one, that I am taking as the D1. D1 is less than D2. And it is having the constant thickness. Only one dimension is changing. Depth is changing. Otherwise, width of the member or the thickness of the member is same throughout. Whatever thickness is here, same is the thickness here. Because of perspective view, it is appearing like that. Otherwise, the thickness is constant throughout. Therefore, what is the area? Area is equal to diameter at that location multiplied by the thickness, that is the cross-sectional area, and is changing from point to point. How to analyze it is the major problem here. For that, what I am doing is, I am considering a small elemental part of this rectangular bar, not the whole length. I am considering a dx so small that whatever the value of depth here is there is almost equal to here. Like if I am considering the whole length, the depth here is d1 and depth here is d2, and their difference is large. Instead of considering the whole length, if I consider only the 50% of the length, what about the difference in depth or the difference in area? Is it reducing, remaining same? Yes. Like I am considering only the L by 2 length. Here the area is this much and here the area is this much. Difference in area, as the depth here is less than this one and greater than this one, difference in depth is reduced when I am reducing the length of the member. So I am considering a very small part, so that within this, whatever the variation in depth is there is constant, almost constant. Means if I observe it from the front side, for the whole length it will appear as a trapezium. If the length goes on reducing, for very small length it will appear as a rectangle, so that I can consider the area constant for that particular length. If area is constant, I need to calculate the area. For that small length, I need to calculate the deformation. For any length, if area is constant and material is constant, deformation is given by P into L divided by A into E. Already we have proved it in the previous class. So we are considering the small elemental part dx at a distance x from one of the end d1. Now I want the area of this small elemental part. I want the area of this part. Area means what is the depth here and what is the thickness here. So I am in need of what is the depth here. What I am assuming is, for this part, the depth is constant. Whatever dx is here, it is d subscript x, and this dx is this length. Length is dx and depth at any location is d subscript x. You should have the clear idea of what is this dx and this d subscript x. So consider small elemental part dx at a distance of x from the end d1. The depth of the small elemental part, if I call it as dx, in the figure it is indicated as d subscript x, and that is given by, yes, how we are calculating it, just see here. Whatever this variation in depth is there, here the depth is d1, here the depth is d1, here the depth is, what is it, d2. Just take the total of these two, d1 plus d2 minus d1 will become equal to d2. Now I am interested, what is the dimension somewhere which is located at distance of x from one of the end. This distance I am interested. How to calculate it? Just here, I can take this particular elevation as combination of these two figures. One is the rectangle and half triangle at the top and half triangle at the bottom. Both, if I club, I will get a triangle like this. This plus this is equal to this figure. I am interested in this length. That length is nothing but this particular length. How to get it? For this figure, for the whole length, depth is constant and is equal to d1. Therefore, it should be d1 plus this particular dimension. How we are going to get this dimension? Just see here, this triangle and this triangle are similar triangles. I am interested what is this dimension. For that, use the similar triangle properties. Yes, the sides are in proportion. That is d2 minus d1 divided by total L is equal to this divided by x. Right? For a total length of L, change is d2 minus d1. But I want it for a length is equal to x. What is it? d2 minus d1 divided by L into x. Therefore, total depth here is equal to d1 plus d2 minus d1 divided by L into x. Yes, friends, any doubt here? Yes. The depth at any location dx is given by dx is this depth is equal to d1 plus d2 minus d1 divided by L into x. dx is equal to d1 plus d2 minus d1 divided by L into x. Right? If this is the depth at this location, what is the area at this location? Area is nothing but the depth multiplied by the thickness. If the area at this location is AX, then AX is given by, if AX is the cross-sectional area of the small elemental part, then the deformation of the part is given by, first you should know what is the AX. AX is equal to dx, d subscript x, depth multiplied by the thickness, dx into t. AX is equal to. Then what is the value of the deformation in the small part? Deformation in the small part is given by deformation in the small part, d. dx part, deformation is given by, what is the formula for the deformation? P into L divided by A into E. Del D is the deformation in the small part, change in length of the small part. Only this part I am taking. Where is this part? It is at a distance of x from one of the end, and length of that part is equal to dx. Yes, length of the part is equal to dx. Therefore, what is the change in length? Change in length is given by del L is equal to P into L divided by A into E. Now, for in this part, change in length is del D. Like that, if I consider one more part, again which is at a distance of x, the expression for the del L will remain same. expression for del D will remain same. Therefore, I need to integrate it from one end to the other end. So, integration, I need to integrate it from x is equal to 0 to x is equal to L. Yes, the elongation of the entire length is given by delta is equal to integration of del D, that is equal to del D is given by P dx divided by Ax into E. Del D is equal to P dx divided by Ax into E. Therefore, integration of it from one end to the other end, that is 0 to L, 0 to L, P dx divided by Ax into E, that is equal to 0 to L, P dx. What is the value of Ax? Substitute the value of Ax. Ax is nothing but the small elemental parts depth, that is nothing but the d subscript x into thickness T into E. Before going for the integration, just see here which are all the constants and the variables. Here P is constant, T is constant, E is constant. Only dx is changing. Only dx is changing. Therefore, integrate it from one end to the other end, 0 to L. What is the integration of 1 divided by dx into dx? 1 divided by dx into dx. Here I am substituting the value of dx here. Dx is d1 plus d2 minus d1 divided by L into x. Yes. Now integrate it. What you are going to get? Delta is equal to P is constant, T is constant, E is constant. What is left out? First you have to integrate this term 1 divided by dx. What is the integration of 1 divided by dx? Log of dx. Log of dx. The value of dx is d1 plus d2 minus d1 divided by L into x. Yes, what else you are doing in integration? It is not a direct function of x. That is why we are differentiating it with respect to the x and we are dividing it. So whatever dx is there, that is to be differentiated with respect to the x. Differentiation of dx in the sense d1 plus d2 minus d1 divided by L into x. Differentiation of this one with respect to x is d1 is 0, d2 minus d1 divided by L into x is equal to d2 minus d1 divided by L. That is to be divided. Therefore, it is d2 minus d1 divided by L. Once again, I will repeat here. P is constant, we are taking it out. T is constant, we are taking it out. E is constant, we are taking it out. Left out is integration from 0 to L dx divided by d subscript x. Yes, integrate it. Integration of 1 divided by dx is nothing but log of dx, that is this term. Next, you need to differentiate the dx with respect to the x and divide it. Differentiation of dx with respect to x, value of dx is this term. Differentiation of this one is d2 minus d1 divided by L. d2 minus d1 divided by L. That is to be divided, means that comes in the numerator. d2 minus d1 divided by L will go at the top. Therefore, your value will become like this. We need to substitute at the limits. Limit is 0 to L. Carefully observe this one. this term as it is as constant. Now I need to go for the integrals. When I substitute the upper limit here, x is equal to, when I substitute, what happens? This L and this L will cancel. What you are going to get? Log of d1 plus d2 minus d1 means you are going to get log of d1, log of d2. d1 minus d1 will cancel out. First term is log of d2. When you substitute the lower value, x is 0 means this term will cancel out. Left out is log of d1. Therefore, final answer is p into L divided by t into E. d2 minus d1 log of d2 minus log of d1. What is it? Log of d2 by d1. Yes, upper limit when you substitute, L and L will cancel out, d1 and d1 will cancel out, left out is d2, log of d2, minus lower value you are substituting 0. Therefore, when this term becomes 0, log of d1. So, if you simplify it, p into L divided by t d2 minus d1 log of d2 minus log of d1, which is finally this value, p into L divided by t d2 minus d1 log of d2 by d1. This formula you are supposed to mug it, by heart it. Yes, as this expression happens to be very important one, that is why I am taking the utmost care. Too slowly I am going till I will repeat the procedure once again. Yes, anybody has got any doubt? Okay. Deformation of tapering rectangular member. I am considering a rectangular member. Of length L, diameter at one end is d1 and at the other end is d2, and d1 is less than the d2. As the cross sectional area is changing, I cannot directly use the formula p into L divided by A into E. That is why what I am doing is I am considering a small elemental part of this particular length dx, so that within this length the change in depth is almost constant and is equal to d subscript x. Now to calculate that d subscript x, I want this particular dimension based on this and this. This we are calling it as the interpolation in the surveying. Yes, this dimension I want. For that what I am doing is d1 plus d2 minus d1 divided by L into x, similar triangle property. Therefore, that depth is given by dx is equal to d1 plus d2 minus d1 divided by L into x. If Ax is the cross sectional area of the member, what is the value of Ax? Cross sectional area of the member, that is given by depth, as it is rectangular one, multiplied by the thickness, that is equal to dx into t, where dx is nothing but this value. Then the deformation of the small part is given by, so I got p, I got L is dx, I got A is equal to Ax. Therefore, deformation of the small elemental part del d is given by, yes, p into dx divided by Ax into E. del D is equal to P into dx divided by AX into E. Repeatedly he is asking in the final exam. That is why I am going too slow. Elongation over the entire length is given by, you just integrate that one. Delta is equal to integral of d delta, that is equal to limit 0 to L P into dx divided by AX into E, that is equal to 0 to L P star dx divided by AX is nothing but dx into T over E. Yes, P, T are constant, you are taking it out. Delta is equal to P into L divided by T, T2 minus T1, and integration of 1 divided by x is log of x. X in place of x we are having the dx, d subscript x. Yes, so afterwards I need to differentiate this one and divide it, so that you will get delta is this one. Substitute the values of the limits 0 to L. Finally, delta is equal to P into L divided by T d2 minus d1. Log of d2 minus log of d1. Therefore, delta is equal to P into L divided by T d2 minus d1 log of d2 my d1. Yeah, what about the screen? Is it visible or not?
Visible, sir.
Friends, screen is visible or not?
Yes, sir. Visible.
Yes.
Yes, sir.
What is there on the screen now?
Deformation of
deformation of tapering bar. Yes.
rectangular.
Deformation of tapering. It is not rectangular. Rectangular we have finished. I am supposed to do the correction here. Deformation of
Another figure,
tapering circular member.
Yes, sir. Circular
Deformation
figure
of
consists.
tapering circular member. Only these two derivations are there. Bit problematic for you in the examination. That you need to practice. That you need to practice. Yes. Again the same thing. We are considering a circular member uniformly tapering. At one end the diameter is d1 and at the other end the diameter is d2. Length is L, depth is d subscript x. Again the area is changing. We are considering a small elemental length dx at a distance x, so that in this part the area is almost constant. Area is almost constant. Let d subscript x, same thing we are doing. D subscript x is the depth here. The same thing we are repeating here. Consider it should be the circular tapering bar of length L with the diameter d1 at one end, d2 at the other end, and we are taking d1 is less than d2, and constant thickness, it is not constant thickness, it is here thickness won't come into picture, circular, subjected to an axial load as shown in the figure. Now consider the small elemental part dx at a distance x from the end d1. From the d1 we are considering a distance is equal to x. Here we are calculating the diameter of the member, and that we are calling it as the d subscript x. The diameter of the small elemental part dx is given by the same as the earlier problem. Dx is d2 minus d1 divided by into x divided by L plus d1. Diameter dx is given by d1 plus d2 minus d1 divided by L into x. Now, if Ax is the cross-sectional area, what is the value of Ax? Ax is nothing but it is circular one. That is why Ax is 5 dx square by 4. dt is wrong here. It should be pi dx square divided by 4. And the deformation formula is again same. Deformation of the small elemental part is given by del d is equal to p into dx divided by ax into e. Yes friends, see here the correction. Ax is equal to dx square pi d square by 4. This t is to be corrected there. Then the elongation of entire length is given by same as the earlier one. Integrate from one end to the other end. Integrate from x is equal to 0 to x is equal to L. Yes, delta is equal to integral of del d, that is equal to 0 to L p dx divided by ax into e. P dx divided by ax into e, that is equal to integral from 0 to L p into dx. What is the value of ax here? This is what the difference here. Ax is given by 5 dx square divided by 4 into e. It is d subscript x. What is the depth of that circular shaft at a distance x from one of the end? Depth of the circular shaft at a distance x from one of the end. Yes, that already we have calculated it. So here what are all the constants? One is p, 4p, 5e are constants. Only variable is dx square. Friends, what is the integration of 1 divided by dx square? This I can take it as dx raised to minus 2. What is the integration of dx raised to minus 2? That is nothing but dx raised to minus 2 plus 1 divided by minus 2 plus 1. Right or not? X raised to n integration of is nothing but x raised to n plus 1 divided by n plus 1. Like that it will become 4p 5e. With patience I am telling you, because the derivation may be of 4 or 5 steps or something like that, but repeatedly is asking in the examination in the part of theory question. That is why these two derivations are very important for you. So it is 0 to L 4p, 0 to L 4p. Here I have substituted the value of dx. Dx is, yes, d1 plus d2 minus d1 divided by L into x. This already we have seen in the previous case also, here also. Whole square divided by 4 into e. Yes, further simplify it. Yes, here it is bit confusing one. 4p is constant, he has taken it out. 5e is constant, he has taken it out. Here actually minus is there, it is not appearing. Means integration of x square, 1 divided by x square I want. That is nothing but x square minus 1 minus 2 plus 1, x raised to minus 2 plus 1, that is nothing but a x raised to minus 1. That minus 1 comes down, that is nothing but, I can say, what is the integration of dx? Dx raised to minus 2, that is dx raised to minus 1 divided by minus 1. That minus 1 comes out, and dx raised to minus 1 is nothing but 1 divided by dx, that is this term. Yes, what is left out? Then I need to take the differentiation of the dx. I need to divide it. D subscript x. I need to divide it. Yes, like the integral of sine of 2 theta. What you are doing it? Sine of 2 theta divide by 2. 2 theta is differentiation. Like that we are making the differentiation of dx and taking it in the denominator. That is 0 plus d2 minus d1 divided by L into x, and its differentiation, this will become 0, and d2 minus d1 divided by L is coming here. Yes, I need to substitute the limits of the integration, 0 to L, 0 to L. Yes, substitute it. Rearrange the terms. 4p, this L is coming here, 4pL divided by phi e, d2 minus d1 is there. Go for the upper limit. Upper limit, what you are going to get? L, if you substitute here, what happens? d1 and d1 will cancel out, 1 divided by d1 is left. 0 if you substitute, this whole thing will cancel out, 1 divided by d1 is left. Therefore here left out is, after substituting, all these terms will be there, 4p divided by phi e, 1 divided by d2 minus 1 divided by d1. 1 by d2 minus 1 by d1 is nothing but d1 minus d2 divided by d1 into d2. That d1 minus d2 and d2 minus d1, they will cancel out each other, cancelling this negative sign, and left out is, here you just see here, yes, 4p is there, phi is there. First we are taking this term, L divided by d2 minus d1, left out is, substitute the upper limit. Upper limit is L. If I substitute here L, this L and this L will cancel out. D1 plus D2 minus D1 will be left out. That is D1 and D1 will cancel out. D2, 1 divided by D2 is the upper limit. Go for the lower limit. Yes, put x is equal to 0 here. This whole term becomes 0 and 1 minus D1 is left out. Yes, you simplify it. Finally, you are going to get 4p divided by phi e, 4pl divided by phi e into d1 minus d1 into d2. Just check out this formula, whether it is right or not, how you can verify it. If d1 equal to d2, what happens to this formula? Just see. d1 equal to d2, then you are going to get p divided by phi d square by 4 divided by E into L, that is P into L divided by pi d square by 4 is nothing but the area of circular member. P into L divided by A into E means indirectly D1 is equal to D2, that I am saying you. That will give you the deformation of uniform circular shaft. These two derivations are very important for you. Therefore, if at all you are having any doubt here, please stop me for the clarification. Yes, anybody has got any doubt? If not, we shall conclude the today's session here. From tomorrow onwards, we shall go for the university
Sir.
problems, question papers.
Hello, sir.
Yes.
ಸರ್ ನೋಟ್ಸ್ ಕಳಿಸ್ತೀರಿ ಸರ್ ನೀವು?
ಅದೇ ಈಗ ಇವತ್ತಂತೂ ಇದನ್ನು ಕಳಿಸ್ತೀನಿ ನೋಡಿ, ಡೆರಿವೇಶನ್ ಇವತ್ತು ಹಾಕ್ತೀನಿ.
ಎರಡು ಡೆರಿವೇಶನ್ ಹಾಕ್ರಿ ಸರ್.
ಅದ್ರೊಳಗೆ ಹಾಕತ್ತೀನಿ.
ಹಾಂ ಸರ್.
ಸ್ವಲ್ಪ ರೆಕಾರ್ಡಿಂಗ್ ಪ್ರಾಬ್ಲಮ್